I am Ryan Loomis, and I'm at the Harvard-Smithsonian Center for Astrophysics, and I'm going to be talking today about uncovering dust substructure and chemical complexity in protoplanetary disks. So thank you, Sunny, for the introduction there. So basically, what I want to talk about today is with protoplanetary disks, there's two main things that are relevant for astrobiology. The first is that, as Sunny mentioned, protoplanetary disks are kind of the middle stage in between when you start off from a cloud and then it starts to collapse down and form a star. The protoplanetary disk forms from the angular momentum of the material around the star, and that's going to include all the material that eventually becomes planets, comets, everything in the solar system. So anything that you care about in terms of exoplanets, et cetera, is coming from a protoplanetary disk. So that's the first thing that I'm going to talk about is basically what the dust substructure looks like and what that tells us about planet formation. The other thing that I want to talk about is how the planetary initial conditions, and that includes all the chemical conditions, are set by the conditions in the protoplanetary disk. So all the chemistry, all the chemicals that end up onto comets, that end up into exoplanet atmospheres, et cetera, they're coming from the disk. So the question is really one of inheritance. If you have chemicals in the diffuse clouds and the dense clouds, how do those get transmitted through the disk and into comets and eventually delivered to planets? Because we know that there are things like amino acids or other more complex species on comets, and we also see complex molecules in diffuse clouds. But the question is really, what does that look like in the intermediate stages, and what's going on here, and what actually gets incorporated into comets? What does that look like maybe in other exoplanet solar systems that we haven't had a chance to look at yet? And the instrument that I'm going to be talking about that we're using for most of these studies is ALMA. So ALMA is the Atacama Large Submillimeter Array, and it's down in Chile. It's in the Atacama Desert of Chile, up in the northern mountains there. It's very high up because we want low water vapor to allow us to look using radio frequencies, so millimeter or submillimeter frequencies, to look at these disks. That allows us to do two things. One is by looking in the millimeter, we're probing dust grains that are approximately a millimeter in size. So these are little tiny dust grains that are floating around that are eventually going to coalesce and form planets. The other thing that we can do is that molecules emit in the millimeter and centimeter frequencies using rotational spectroscopy. So we can use rotational spectroscopy to look for these molecules and see their signatures and fingerprint them so that we know what's present in these disks. So as Sunny mentioned, ALMA is completely revolutionizing our understanding of protoplanetary disks. So this is a really simple cartoon of what such a disk would look like. This is like an edge-on view, and this is a top-down view. This is what we used to think was going on, because these were observations from, say, the submillimeter array in Hawaii, the SMA, which is kind of like a precursor to ALMA. So these were originally the images of what we thought was going on. We thought that these disks were quite basically full, completely filled in with dust, and then a flared kind of gas disk around it. However, ALMA, you can see that the beam size here this is like our resolution element, has gone from this large beam to this absolutely tiny beam. ALMA has completely blown this out of the water. So now we can see that where originally we had no idea that there were all those rings, now we can see all of these nested rings in both disks like HL Tau and TW Hydra, and we know that there's all this substructure in the disk. So I'm going to talk about a new disk in which we've seen some of the substructure and what we might take away from that in terms of what's causing these gaps. So there's going to be a talk later talking about how magnetic fields might play into that. And there's a lot of possibilities as to what's going on with this. But one thing that's been proposed, and it was thought about for a long time before we actually observed it with ALMA, is that planets, as they go around, they're going to basically shift the dust around, kind of like blow it out of the way and suck it in where they have gravitational pull on it. And they're going to cause pressure traps that basically carve out these gaps and rings in the disk. So I'm going to talk about this object AA Tau, which is a pretty unique disk that's been studied for a long time, since the early 90s. And one of the things that we look at when we look at stars is we're trying to understand not only what the properties of the star are, but what do those properties look like as a function of time. So what we do is we measure the brightness of the star as a function of time, and that tells us something about what's going on. So this is used for the transit method of detecting exoplanets, but it's also used to find a bunch of other features about what's going on with the star, its magnetic field, et cetera. And so people were monitoring AA Tau back in the 90s, and they noticed that it had this weird short-term variability, and they've also noticed more recently that it has a weird long-term dimming trend. So I'm going to talk a little bit more about those later, but right now the kind of takeaway to start with is that people thought that the short-term variability was caused by a highly inclined disk, so that means that its geometry when you're looking at it is that it's quite edge-on, and that it had this little warp in the center, and that warp is basically blocking out the light that's that you're looking at from the center of the star there, and that goes as a function of time as it rotates around, and that's causing these little dips. So for right now, the takeaway is that A tau was thought to be really edge-on. But when we started looking at it with ALMA, it's clearly not edge-on. It's inclined at about like 60 degrees, so that's much more like this rather than edge-on. And it's got weird features. So just like HL tau and TW Hydra, it's got things like this weird little flux bridge. It's got rings here, so there's one ring there, another ring there. The third one's a little hard to see, but you can see it better when I put some contours on it. And so now you can see that there's all these rings in the disk, which are just like HL tau and TW Hydra, where we think that these might be caused by planets carving out those gaps. The other thing that you might notice is with these contours, you can see that it's kind of twisted in the center. It's got that slight twist to it, and I'll come back to that as to a feature that we think might be involved with a feature with exoplanets. So we took this data and we tried to reproduce it with some simple models. The first thing we tried is basically just a series of concentric rings. And that reproduces the observations really well. The observations are in black here with the red dashed lines being our model, so it fits it quite well. But there's systematic residuals left over. And those residuals are negative on either side here and positive on either side there. And so that kind of checkerboard pattern we think might be caused by a warp in the disk. And I'll get to that in just a second. But for right now, we know that by using this simple model, we can show that there are rings in the disk. And like I was talking about before, there's rings in all these other disks, and almost starting to show that there's a whole class of objects at these substructured disks, and all these substructured disks are showing evidence for exoplanet formation directly. Now going back to that slight twist in the center, what we think might be going on here is if I kind of put up a schematic of what we think the system looks like. So there's three rings. There's the star in the center. The star is aligned at about 60 degrees, and the rings are at 60 degrees there, and we're looking at it like this. So that's what we think, schematically it looks like. However, we know that because we see that variability that I mentioned earlier, we know that the inner disk has to be close to edge-on. And the other thing that we know is that there are polar outflows that come out of the jets here. I don't have an image of it here, but there are jets that come out, and we know that those are anti-aligned with the disk. So rather than being the axis of the star being like this, the axis of the star is actually aligned this way. So this means that the inner disk and the outer disk are actually misaligned. Furthermore, it might be possible that you're getting material that's streaming across from this innermost ring here and streaming across the gap into the star. So that might be associated with that inner flux bridge as those radial flows are moving around the disk. Then that might be causing this flux bridge here. Now that's interesting because there are two features that this might explain. So first of all, we know that these stars have signatures of accretion. So that's basically where material is coming onto the star and feeding the star as it's being formed. That's well observed that a lot of these stars that are in the disk stage still show signatures of accretion. But if you have these gaps in the disk, material needs to be crossing those gaps in order to get onto the star. And that's a problem because the way that these gaps work is they're pressure traps. So you've basically got a gap of pressure, and then everything's kind of pushed up on one side here and pushed up on the other side. So to get material across that, it requires a lot of energy or an instability in the disk. And that's what we think is going on, is that there's an instability in that region in between the innermost ring and the inner disk. There must be some sort of instability here. And that instability can actually be caused by planets. So planets both carve out the gaps, but they can also cause slight instabilities that allow material to stream across and solve the problem. So this is indirect evidence for planet formation directly in this disk. The other thing that this is quite interesting for is that this material that's coming across, as it comes across there, it's going to go across the line of sight that we're observing. So as it comes across the line of sight, it may block out some of that starlight. This is thick dust, so imagine like looking through a cloud of dust. It's going to block out quite a bit of the light, and that might be what's causing this long-term dimming trend. The other thing that's kind of interesting about this is, okay, so you see this setup where we've got the disk that's aligned this way, and that's fine because it doesn't really matter what alignment the system has relative to us, because it can be, all 360 degrees, it doesn't matter for the purposes of planet formation. What is interesting, though, is that the inner disk and the outer disks are misaligned, and that plays a big role in planet formation. One of the main observations from the Kepler project is that they're seeing, one, thousands of planets, but two, they're seeing that these planets don't necessarily always mesh up with radial velocity measurements. So radial velocity measurements are where, rather than watching the transit signatures as a planet goes across in front of the star, you might see signatures of the wobble of the star as a planet tugs on it. So from radial velocity signatures, we sometimes see evidence of large outer planets that are misaligned with the planets closer in towards the star. So if you want to compare this to, say, our solar system, the size here is, not to scale, but the size here would be that this would be our sun, and then all of the inner terrestrial planets would be inside of this inner disk. It's quite small, only a few AU in size. And then maybe Jupiter would be about here, Saturn would be out here, and the Oort cloud would be out here, and the Kuiper belt and the Oort cloud would be out here. So this means that basically you could easily have a giant outer planet out here that's misaligned with the terrestrial planets. In our solar system, they're all aligned, but Kepler is seeing that there are a lot of systems where these are misaligned. So directly having evidence for this sort of misaligned system kind of fills in some of our missing pieces as to how would those systems in Kepler actually be formed. And we're going to be able to test this directly with new observations in the future where we're actually able to go even higher resolution, more comparable to those H.L. Tau observations. And we should be able to see whether this is actually going on or not. The other thing that I want to just briefly touch on is I mentioned that not only are we looking at the planet formation in the disks, but we're also trying to figure out the chemistry that's going into these planets, into these comets that are forming. And for all of the chemists and biologists in the audience, these aren't complex molecules for you guys. But for our purposes, they are, because stellar radiation, interstellar radiation, it'll blast apart molecules, no problem. So most of the molecules that we see in space are quite small compared to what you guys are used to working with. And for our purposes, methanol and methyl cyanide are kind of the first building blocks for being able to form more complex species. So it's really important to be able to trace these and see how do they get incorporated into comets. And very recently, we put out 2 papers that showed for the first time a detection of both methanol and a detection of methyl cyanide. Now the problem here is, so these contours are only 1.5 sigma contours. So these are quite weak detections. And the problem is that basically as you go up in complexity with molecules in space, you get fewer and fewer of them, which makes sense. But that means that as you go to more complex species, they're going to get weaker and weaker, and we're not going to be able to see their signatures as strongly. So to be able to investigate complex chemistry in protoplanetary disks is going to require us to probe much, much deeper, use up more telescope time, which is expensive, et cetera. So something that I've been working on is a new method to pull out these signals with higher signal to noise. So if you're familiar with radar, one of the things that they use is something called match filtering, where basically if you know what your signal looks like, you can convolve it through the data and get out an improved spectrum. So we've used this for our data. So these were the observations of the methanol that I showed. So these were the individual lines. They're very, very weakly detected, less than 3 sigma for each of these. And it's just barely detected in the stack spectrum. But when we apply the match filter to it, we get strong detections of each of the individual lines, and it's over 7 sigma detection of the stacked lines. So that was roughly a 45% signal to noise boost, which sounds like maybe a little bit, but it's not too much. But that actually translates to a factor of over 2 in observing time. So we actually save a lot of telescope time by using this method. And I'm pretty excited we're going to be able to apply this to a couple other studies in the future. And one thing that we're really hoping to do is apply it to spectral line surveys, where we can start to look for all sorts of different lines of complex species and look for ones that we might not have thought would be there in the first place. Already from one of these surveys, we have 5 new molecular detections in that survey. So just as a takeaways from this, using ALMA, we're basically probing two aspects of planet formation and comet formation. One is we're actually probing directly what the structure of the disk looks like. We saw that for AA tau that it's a substructured disk that has those rings and gaps with direct evidence for planet formation, and it's got this warp. The warp might explain misaligned exoplanet systems. And we're also starting to use ALMA to find complex molecules in disks, which proves that they're abundant during the processes of planet and comet formation. And so that means that they might be delivered from those comets onto planets in the future. And then they're usable for all of you guys and all of the other studies that you're doing. So that's it. Questions?
I was just wondering, do you have any hypotheses about how you actually get those warps, how you get the misaligned disks?
Yeah, there's a couple different things that might be going on. AA tau is a little bit weird in this respect, actually, because it's quite easy to form those warps if you have a binary star. And that's been theorized before, that binary stars can basically cause torques that would allow that to happen. It's a little bit harder to do that with a single star system like AA tau. But there's a couple different mechanisms that might be able to work, and there's a few groups that are trying to do theory on that right now. So maybe in about half a year, we should have an answer for that. But there are groups that are working on that.
Thanks.
OK, this is a total hypothetical. I'm not sure if you even know the answer right off the top of your head. But so obviously, with a misaligned disk, you're going to have a change in the way that the starlight is able to illuminate the rest of the disk. Mm-hmm. How do you expect that would affect what chemical species can form in the parts of the disk that are misaligned with that inner center part?
That's a great question, actually. So for one thing, the misaligned inner disk is going to precess. And so that's going to precess on timescales of maybe decades or so. So it's not going to have a huge impact on, say, if a comet is forming at this distance versus that distance. It's not going to totally change the cometary composition. What can happen, though, is that shadowing will cause temperature differences in the disk, which can affect the chemistry dramatically. And that also gives me a chance to talk about a new result that our group has, where we're looking at something slightly different with flares. So a lot of these stars flare quite frequently in the X-ray. And flares, which also can be affected by shadowing and things like that, can dramatically change the chemical composition of the disk, because those flares can irradiate things and completely change them. And that might also affect things like, say, amino acid stability on comets, right? Because these flares can very dramatically affect the chemistry in there and destroy more complex species. So.
You mentioned that you can study rotation of molecules with these radio telescopes, right? Mm-hmm. So is that due to redshift? If yes, can you study vibrational transitions, electronic? And if yes, what's the reason to use other techniques to basically detect molecules?
Yes.
Since radio telescopes are cheaper.
Yeah, so there's a couple different things there. So first, we use radio telescopes. They are a lot cheaper in some respects because you can use radio telescopes on the ground because they're not as affected by the atmosphere. Infrared telescopes and other things need to be pushed up into the in orbit or in space, so that's why JWST is going to be launched into space. Rotational spectroscopy can only probe molecules that are in the gas phase. So that's great for being able to probe things in kind of the gas portion of the disk. What that means is that we aren't able to probe species that are on grain surfaces. So in the kind of middle layer of the disk, these molecules are freezing out onto grain surfaces, and they're going to be incorporated from those grains into comets, things like that. So the planet formation zone is actually mostly frozen out onto grains, and we can't probe that with rotational spectroscopy. What you might be able to do is you could use vibrational spectroscopy to probe that, but the problem is that you need to have a backlit source in order to do that efficiently. So you need to have a way to illuminate those icy grains from behind, and the only way to do that is a very edge-on disk. And if you have an extremely edge-on disk at maybe 87 degrees inclination or something, it's a very narrow range, then you could use JWST to investigate those ice grains. But it's going to require a very narrow set of parameters. And that's actually one of the reasons that we originally looked at AATOW, because we knew that it was supposed to be edge on. And we were hoping to find a system that might be able to then be used for JWST. There's a couple other target systems that might be able to be used for that.
Hey, I have a question. So what keeps the dust streamers from like getting smeared out? Like why does it rotate rigidly?
Yeah, that's a great question. It doesn't rotate rigidly. That was just because I'm bad at PowerPoint. And I don't do hydrodynamic simulations, so I don't have anything pretty to show. But in reality, it's more of like a vortex type thing. Like I said, it's an instability. So you would get all sorts of swirling streamers. But those streamers might be coherent on timescales of maybe 10 to 20 years. So enough to rotate around and basically cause the features that we're seeing. So. Yeah, so actually that's one thing that we're starting to see is actually, so it looks like that long-term dimming, it's starting to come out of that right now. And if that is happening, then it would basically show that it's one feature that's moving across the face of the disk. And also with the ALMA observations, with the higher resolution observations, we'll be able to make a prediction then as to when it would come back around. So we're hoping to be able to make an actual testable prediction. All right,
Let's
thanks.
thank Ryan again.